Welcome to the Deep Dive. Today, we're dissecting some really cutting-edge work that's aiming to fundamentally change how we generate digital avatars. Forget those elaborate multi-camera rigs. We're talking about creating a realistic, fully animated talking avatar from just a single static image.
Exactly, and that's quite a claim. Current high-fidelity avatar creation pipelines, well, they often demand significant data acquisition, think structured light setups or, lengthy video sequences.
Right.
This introduces practical limitations and can restrict the achievable range and fidelity of expressions and gestures, especially when it comes to the subtleties of, say, facial dynamics and hand articulations.
Exactly, and that's the core problem that the research in One Shot, One Talk, whole body talking avatar from a single image directly tackles. This isn't just about photogrammetry from a single viewpoint, it's about generating a dynamic, controllable avatar capable of nuanced communication.
The ingenuity here lies in their integrated approach. They're simultaneously addressing two key challenges: the complex problem of modeling dynamic human movement and the need for the resulting avatar to generalize to novel, unseen gestures and expressions.
And all starting from a single visual input.
All from that one picture.
Okay, let's break this down. What are the inherent limitations of the prevailing avatar creation methodologies that make this single image approach such a, potentially disruptive advancement?
The established methods, as we touched on, typically necessitate extensive input data. We're talking minutes, maybe even hours, of synchronized multi-view video or carefully controlled monocular capture.
Yeah, the setup alone is intense.
It presents logistical hurdles and considerable costs. And what's more, despite all this data accurately capturing and then animating intricate details, think about the subtle deformations around the eyes during a smile, or the complex kinematics of the fingers often remains a significant challenge.
It's intuitive, really.
Yeah.
If a particular hand configuration hasn't been recorded from multiple angles, the system will struggle to synthesize it convincingly.
Absolutely. And the generalization aspect is equally critical for creating truly versatile avatars. Existing systems often falter when asked to generate novel movements or expressions that weren't adequately represented in their training datasets.
Like dynamic clothing.
Exactly. Or consider the realistic simulation of flowing clothing or the intricate dynamics of the inner mouth during speech. These are notoriously difficult to get right. Starting with just a single static image only exacerbates this problem, as it inherently lacks temporal information about potential movements.
So how does this one-shot, one-talk pipeline tackle these fundamental limitations? What's the core architectural innovation that allows them to bridge this significant data gap?
Their strategy is quite clever, actually. They employ a two-pronged approach to these identified challenges. For the generalization problem, the ability to produce new motions, they leverage recent advancements in pose-guided image-to-video diffusion models.
Diffusion models, okay.
These are essentially generative AI models that can take a static image and a sequence of body poses as input and synthesize a plausible video of the person performing those actions.
So they're basically generating synthetic motion sequences to drive the animation, like creating fake training data.
Precisely. These generated videos aren't perfect, mind you, and the paper aptly refers to the individual frames as imperfect video frames, or pseudo-labels.
Okay.
However, they provide a rich source of motion cues. To obtain a diverse range of human movements, they even tap into the TED gesture dataset, which is a large repository of people speaking and gesturing naturally.
That's an interesting strategy. It's like using a vast database of observed human movement to inform the animation of a new subject. But you highlighted that these are imperfect videos. How do they manage the inherent noise and potential inconsistencies in these AI-generated pseudo-labels?
That's where their second key innovation comes into play. A tightly coupled 3D Gaussian Splatting, 3D Mesh hybrid avatar representation.
Okay, 3D and Mesh.
Yes. This is the core of how they address the complex dynamic modeling challenge posed by these noisy pseudo-videos. Instead of relying solely on the synthetic video, they intelligently combine the strengths of two distinct 3D representations.
3D Gaussian splatting and a traditional mesh structure. How are these two complementary representations integrated in their pipeline? What does each bring to the table?
Well, the mesh provides an underlying geometric prior, a fundamental understanding of human shape and skeletal articulation. Think of it as providing the basic structure, the skeleton almost.
So a foundation.
3D Gaussians, on the other hand, excel at representing fine surface details and achieving photorealistic rendering quality. By tightly coupling these two, they leverage the structural robustness of the mesh with the visual expressiveness of the Gaussians.
And the single input image ties it all together appearance-wise.
Crucially, yes. They use that single input image to inform the appearance properties of this hybrid representation, ensuring identity preservation.
That makes intuitive sense. The single image defines the visual identity, the pseudo-video suggests the possible motion dynamics, and the hybrid representation provides a framework to effectively combine this information. Let's get into some of the specific technical components and innovations that underpin this pipeline.
Okay. A central aspect is this coupled 3D Mesh avatar. The mesh component is based on the SMPL-X model, which is a sophisticated parametric human body model encompassing body, hands, and facial geometry.
A standard but powerful choice.
Very much so. They initialize a dense cloud of 3D Gaussians directly onto the surface of this canonical SMPLX mesh using UV parameterization. This essentially establishes a correspondence between points on the mesh surface and the individual 3D Gaussians.
So the Gaussians are effectively anchored to the underlying digital human model.
Right.
Textures almost.
Not rigidly fixed, but highly coupled, yes. They then introduce two distinct deformation fields, one that acts on the 3D Gaussians and another that deforms the underlying mesh.
Two deformation fields, okay.
And a critical aspect here is the application of regularization terms, specifically to the mesh deformation techniques like Laplacian smoothing, to maintain surface smoothness and normal consistency to prevent excessive distortion.
So keeping the mesh well-behaved.
Exactly. And these constraints imposed on the mesh deformation indirectly guide the deformation of the associated Gaussians, promoting a coherent and geometrically plausible avatar, even when driven by the potentially noisy pseudo-videos.
It sounds like a very effective way to introduce structural constraints into the deformation process. What about the generation of the pseudo-labels themselves? What specific models do they employ?
They utilize two distinct pre-trained models, both driven by motion sequences derived, as mentioned, from the TED gesture dataset. For generating the body and hand gestures, they employ MimicMotion, a model known for its strong performance in hand articulation.
Right, hands are tricky.
Very. And for synthesizing facial expressions, they leverage Portrait4D v2. Both of these models take SMPLX pose parameters as input and generate the corresponding synthetic video frames that serve as our pseudo-labels.
And you mentioned their departure from standard pixel-wise error metrics when supervising with these pseudo-labels. That seemed important.
Correct. It's quite crucial. Because the pseudo-labels can contain artifacts and inconsistencies inherent to the generative process, direct supervision using per pixel losses like L1 or mean squared error can lead to undesirable blurring and a loss of identity in the final avatar.
Right, averaging out the noise leads to mushiness.
Precisely. Instead, they primarily rely on a perceptual-based loss function called LPIPS, which extracts deep features from a pre-trained VGG network. This loss focuses on higher-level structural and visual similarities.
So he's more like a human.
In a way, yes. It makes it significantly more robust to the imperfections in the pseudo-labels and ultimately results in improved overall appearance modeling.
That's a key insight. It's about capturing the perceptual similarity rather than achieving exact pixel-level alignment with potentially flawed data. But they also have the single clean input image. How is that leveraged during training?
Good point. For the single input image, which provides the high-fidelity ground truth appearance of the target individual, they do employ per-pixel supervision using standard loss functions.
Okay, so direct supervision there.
Yes. This includes L1 loss to ensure color accuracy, SSIM, structural similarity index measure, to maintain structural coherence with the input image, and a mask loss to ensure the generated avatar silhouette accurately matches the person in the photograph. This direct supervision anchors the avatar's identity firmly to the initial visual information.
Makes sense. You need that strong anchor. And just to get a sense of the implementation scale, what's the approximate number of Gaussians they utilize, and what's the resolution of the UV texture map?
They report using approximately 150,000 anisotropic Gaussians. Interestingly, they simplify the individual Gaussian parameters by fixing their opacity and rotation, and primarily optimize a scalar scaling factor for each Gaussian.
So fewer parameters to optimize per Gaussian.
Exactly. This likely contributes to training stability and improved generalization. They also utilize a UV map with a resolution of 512 for texture representation.
Okay, so we have a detailed picture of this sophisticated pipeline. How does it actually stack up against existing state-of-the-art methods in terms of performance? The results.
The paper presents a pretty comprehensive evaluation, including both qualitative visual comparisons and quantitative metric analysis. Qualitatively, as illustrated in their Figure 3, when they compare their method against leading approaches like ExAvatar, ELICIT, and MimicMotion.
Some heavy hitters there.
Definitely.
Yeah.
In cross-identity motion reenactment scenarios where they animate one person's avatar using the motion of another individual, their method demonstrates significant advantages. It notably preserves the identity and fine-grained details of the target individual much more effectively, particularly in challenging regions like the hands and face.
And Figure 4, that showcases comparisons for self-driven pose reenactment, right? Where the avatar is driven by motion captured from a video of the same person.
Correct. And even when compared to methods that are trained on actual multi-view video data, their one-shot approach exhibits a remarkable ability to accurately model both facial expressions and hand movements while maintaining strong identity consistency with the single input image.
That's impressive, especially given the limited input. And what about the objective metrics, the quantitative comparisons presented in Table 1?
Quantitatively, using standard metrics such as MSE, mean squared error, L1 distance, PSNR, peak signal to noise ratio, SSIM, and that perceptual LPIPS metric.
Right.
Their method achieves superior performance compared to the baseline methods on self-driven data. This indicates that their approach not only produces subjectively more realistic avatars, but also achieves lower pixel level errors and higher perceptual similarity to the ground truth.
The ablation studies they conducted are also crucial for understanding the contribution of individual components, aren't they? What were some of the key findings from those experiments?
Yeah, ablations are always revealing. They clearly underscore the importance of several key aspects of their pipeline. For instance, as shown in Figure 7, they demonstrate the significant impact of the mesh-related constraints.
The Laplacian smoothing and normal consistency.
Exactly, those, as well as the Gaussian Laplacian loss. Removing these components leads to noticeable geometric artifacts and a loss of fine surface details, highlighting the critical role of the mesh in maintaining structural integrity.
So the mesh really holds things together geometrically. And Figure 6 focused on the role of the perceptual diffusion guidance, if I remember correctly.
Yes, that ablation study convincingly demonstrates that utilizing the pose-guided diffusion models to generate the pseudo-labels and subsequently supervising the training with the perceptual LPIPS loss is essential for effectively in-painting regions that are occluded or unseen in the original single image.
Filling in the back of the head, for instance.
Precisely, and for synthesizing natural-looking textures in these disoccluded areas. Without this guidance, the avatar tends to overfit to the visible regions of the input image and struggles to convincingly generate plausible content for the unseen parts.
And the retracking step they incorporate. Figure 8 sheds light on that. What's its purpose?
Right, the retracking. By employing this retracking step to refine the poses in the generated pseudo-videos, they can significantly mitigate the temporal inconsistencies and misalignments that can be introduced by the 2D diffusion models.
So cleaning up the generated motion.
Essentially, yes. This refinement leads to a much better preservation of texture accuracy and prevents the blurring of details that occurs without this crucial post-processing step.
Of course, all research has inherent limitations. What are some of the challenges and potential avenues for future work that the authors themselves acknowledge?
They're quite upfront about it. They point out that their method currently relies on a robust and accurate initial registration between the input image and the underlying SMPLX mesh.
The initial fitting.
Yes. In cases where this initial fitting is suboptimal, particularly in complex articulated regions like the fingers, it can lead to propagation of errors during the subsequent optimization and potentially result in inaccurate textures or geometric distortions.
I can see how bad initial alignment would cause problems downstream.
Definitely. They also note current performance limitations when dealing with very large or unusual viewing angles, likely due to the inherent biases in the human motion diffusion models, which are typically trained on more conventional camera viewpoints.
That's an understandable limitation, as generating plausible novel views remains a challenging problem in computer vision generally.
Absolutely. Looking towards future research directions, they propose several promising areas. One is the integration of semantic information derived from large language models.
That's interesting. LLMs for gesture.
To potentially guide the generation of more contextually appropriate and expressive gestures and speech patterns. Another direction they suggest is the incorporation of static priors obtained from traditional 3D reconstruction techniques to further refine the initial geometry and appearance of the avatar.
So combining this with other 3D capture methods. Okay.
Yeah.
This research clearly represents a significant step forward in the field of avatar generation. To summarize, what would you say is the key innovation and the most impactful contribution of this one-shot, one-talk approach?
I think the core breakthrough is really the ability to create a highly realistic and animatable whole-body talking avatar using only a single static image as input. This significantly democratizes the process of digital avatar creation.
Makes it much more accessible.
Exactly, making it potentially accessible to a much broader range of users and applications.
And consider the implications for emerging technologies like AR and VR, advanced telepresence systems, and more immersive forms of remote communication.
Indeed. The fundamental innovation, I'd say, lies in their tightly coupled 3D GS mesh hybrid representation combined with the ingenious use of imperfect pseudo-labels generated by diffusion models and guided by that crucial perceptual loss function.
Yeah.
It's a very elegant and effective way to leverage the complementary strengths of different AI and computer graphics techniques to overcome a significant challenge in the field.
It certainly provides a fascinating glimpse into the future of digital representation. Considering the rapid advancements we're seeing, what novel forms of digital communication and interaction might become commonplace thanks to these increasingly sophisticated avatar technologies? That's certainly food for thought. Thank you for sharing your expertise with us today.
My pleasure. It was great discussing it.